Welcome back. Today we're going to be having lecture number 22, which is entitled Particles and Waves. Now, last time we'd been looking at special relativity, and special relativity basically is the area of physics that deals with things moving very, very fast. Fast, kind of like on the order of the speed of light. Today we're going to be starting in an area that's called quantum mechanics, and that's basically the area of physics that deals with things that are very, very small. In other words, kind of on the order of the size of an atom or even smaller, some subatomic particles. So first, I'd like to start by thinking about a source of light. Now, one of the things we were thinking about, that we talked about back when we were looking at interference and diffraction, was what happens when light, like a laser, goes through a double slit or a single slit, and we see the kind of interference pattern that we get when we have that kind of source of light. Now, I'd like to look at another kind of light source. This is just an incandescent light bulb. When we plug this in, it heats up and starts to glow. The filament in there starts to glow. It gets very hot. And I'd like to think about what is the light like that is created by an incandescent bulb. Well, what's going on here? We've got electricity flowing up and down this filament. So we've got a filament basically, and we've got current, electrons basically, moving up and down this wire. This is connected to an AC source. We've got them going up and down 60 hertz, 60 times a second. But actually these electrons are moving in a very random fashion all over the place, and then are just kind of drifting up and drifting down and drifting up and drifting down on top of this very random motion with this drift velocity changing every 60 times a second. Now, because we've got these currents moving all over the place and changing, we've got these changing electric fields, changing magnetic fields, and these are creating these electromagnetic waves that we then see as the visible light. Now, if we could take that light and break it down into its constituent colors and see what kind of energies are being created at all of these different wavelengths, we get a very, very interesting spectrum that looks something like this. This is actually a simulation that's put out by the University of Colorado in Boulder, and they have some great simulations that you can play around with, and they're all free. If you want to just go to phet.colorado.edu. Now, what I want to show you here is the kind of light that a light bulb would emit. This is actually a graph of the wavelength down here, shorter wavelengths here, longer wavelengths up here, and then the amount of energy that's being given off on the vertical axis. What we see, this curve here, this shows us that the light that's given off by a light bulb, it peaks over here outside the visible range of our spectrum. So these are the colors of the rainbow that we can see with the naked eye, what we would call visible light: red, orange, yellow, green, blue, indigo, violet. And what we find is that the light bulb actually peaks out here in the infrared end of the spectrum, but it's giving off a lot of visible light. And when we have a lot of visible light of all different colors, it looks like white light to us. Now, what happens is when something heats up or gets even hotter, what I want you to notice is a couple things. We'll heat this up more. So we can come over here and look at hotter objects. So we'll raise this up, and oh, it goes off the screen because the hotter the object is, the more energy it gives off. So we can shrink down this scale here. And what we find is that if we go up, say, to the sun, we find that the peak has moved from the red end down into the visible light, down here in the greenish area of the spectrum. So we still have a lot of light of all the different colors, but we've got even more light coming out everywhere. We've got a lot of infrared, and now we've got some ultraviolet over here too. Now, this particular curve is what we call a blackbody spectrum. Now, we've talked about blackbodies before, in particular back in 1111 when we started talking about the methods of heat transfer. We talked about convection, conduction, and radiation was the light given off by a heated body, and we talked about the blackbody spectrum. So that's what is being given off here. Now, it was a major problem in the early part of the 1900s to understand exactly where this shape came from. Where did this black body spectrum shape come from, theoretically? Well, that was a big problem. So this black body spectrum curve was actually explained by Max Planck in 1900. Now, to do it, he had to come up with a very, very strange idea, and that is that the energy in the electromagnetic spectrum was set in small little bundles, that you couldn't have a continuous amount of energy at, say, a particular frequency. You could only have certain amounts of energy in these little discrete quantities that were called quanta. And one quantum of a particular frequency of light had an energy that was proportional to the frequency with a constant of proportionality called h, which we now call Planck's constant. So that the energy of one quantum of light was equal to hf, and h had a value of 6.626, or it has a value of 6.626 times 10 to the minus 34 joule seconds. So let's figure out what's the energy of one quantum of, let's say, red light with a frequency of 4 times 10 to the 4th hertz. So that would be an energy of 6.626 times 10 to the minus 34 joule seconds, h, times the frequency, 4 times 10 to the 14th, or 2.65 times 10 to the minus 19th joules. Now, I want us to just notice something about this. That is a very, very small energy. So although this energy in the electromagnetic field is quantized, in other words, it's divided into small individual amounts, you can't have, say, a half of a quantum of red light. You can only have one quantum, or two quanta, 3 or 4 or 5, something like that, an integer number, a counting number actually, and 0, of quanta of a particular color of light. You can't have half of one or a third of one. But the energies of each one, the energy of each one is very, very small. So it's hard to notice the fact that the light is quantized. It seems smooth. We seem to be able to have any amount of energy that we want because the amount that it's quantized in is so small. It's kind of like having a drink of water, and you know that the water is actually made of little quanta, so to speak, of water, little individual molecules. You can't have a half of a molecule of water. But it seems continuous when you take a drink. You don't notice that you're getting a counting number of molecules of water. It seems like a smooth, continuous material, and you can have any amount that you want. So it's kind of like that. The energy of one quantum is a very, very small amount. Now, at around this time, there was also another problem going on called the photoelectric effect. The photoelectric effect occurs when light strikes a metal surface. Occasionally, under certain circumstances, electrons are emitted from that surface. The light comes in and basically knocks the electrons off of the surface. Well, that kind of makes sense. We've got energy coming in. The electrons can absorb that energy, break off the surface. Getting enough energy, they could break off the surface. Those emitted electrons are then referred to as photoelectrons. They're electrons that are emitted because they absorb this light. Now, what kind of properties would we expect these photoelectrons to have? What kind of characteristics, depending on the incoming light and the energy of the electrons? The energy of the electrons can actually be measured if we take these emitted electrons and send them through a potential difference. By varying the potential difference, we can actually determine just what that energy of the electrons are. So what kind of relationship do these quantities have? Well, what would we expect them to have? What we would expect to happen would be that if we increased the light intensity, remember, the intensity basically means the brightness of the light. So if we send in a brighter light source, or more light, we would expect the kinetic energy of the emitted electrons to get bigger. We're sending in more energy, the electrons absorb more energy, they come off with more energy. That's what we would expect. Also, we might expect them to be emitted faster. In other words, when we turn on the light, we wouldn't have to wait as long. The electrons would absorb that energy. Remember, we've got these waves coming in. The electrons absorb the energy. It might take them an amount of time to build up enough energy to have enough energy to break off the surface. So we increase the intensity. We're increasing the amount of energy per second that the electrons can absorb. They might then be emitted sooner. We don't have to wait as long. we decrease the intensity, we have to wait longer for the electrons to be emitted. That's what we might expect. Also, we would not expect any frequency dependence. We know that the intensity of the light is basically dependent on the average electric field amplitude and the average magnetic field amplitude. The energy density is basically related to both of those squared. That has no dependence on the frequency. It doesn't matter how fast the waves are varying, what the frequency is. It only depends on the amplitude of the electric and the magnetic field. So we would not expect any frequency dependence on how these electrons are emitted. Well, as a matter of fact, that is exactly not what was seen. What we actually see is that if the frequency is too small, in other words, if it's below some critical value, some cutoff value, we don't get any photoelectrons at all. None are emitted, no matter how long we wait. If the frequency is greater than this critical frequency, this cutoff value, then the photoelectrons are emitted immediately. We don't wait at all. If the frequency is high enough, electrons are emitted as soon as the light is turned on. If we increase the intensity of the light, so if we make it a brighter source, we get the same kinetic energy for the electrons, but we get more of them. So increasing the intensity means we get more photo-emitted electrons. If we decrease the intensity, we get fewer. Increasing the frequency past the critical value actually increases the kinetic energy. So the larger the frequency, as long as it's larger than the critical value, increases the kinetic energy. Now this is very, very different from the view that we have had of the electromagnetic field that we've been talking about prior to this lecture. How are we going to explain this photoelectric effect? Well, Albert Einstein did that, and for which he won the Nobel Prize in 1921. Einstein's explanation of the photoelectric effect uses the same idea of light, this quantization of light, that Max Planck did for the blackbody spectrum. Let's imagine that the light coming in from our light source is made of these quanta of light, each one having an energy that's proportional to the frequency E equals hf. Now, each electron is bound onto the surface of the metal by a certain amount of energy that we'll call the work function, W sub O. Now, the energy of the energy of the light comes in, of one bundle of light comes in, is absorbed by one electron. Now, if that light does not have enough energy to knock the electron off of the surface, in other words, if the energy of one bundle is not larger than W sub 0, the electron is not emitted, and it's never emitted. But if this is larger than W sub O, the electron is able to be knocked off, and the amount of energy that it then has left over as kinetic is the difference between what it was given by the light minus what it had to use to get off of the surface. So the kinetic energy of the electron is then equal to hf minus W sub O. Now notice, if hf is less than W sub O, we're not going to get any emitted electron. It's not going to have a negative kinetic energy. It's not going to be emitted. So what's that cutoff frequency? Well, that would be when hf critical is equal to W sub O. In other words, F critical is equal to W sub O over H. As long as the critical frequency is greater than this W sub O, the work function over H, we'll get emitted photons. Emitted electrons. So how does this explain all of what we talked about before? Well, first of all, by increasing the intensity of the light, what does that mean? In terms of these little bundles, which I'll now use the term we use now, one little bundle of light, rather than being called a quantum of light, we refer to it as a photon. So each photon of light has an energy that's equal to, hf, where f is the frequency of that light. So when we increase the intensity of the light, what does that mean in terms of photons? It means we're sending in more photons. So at a particular frequency, if we increase the intensity, we're sending in more little bundles, more photons. More photons means more electrons, as long as the frequency is greater than the critical frequency. If the critical frequency is less than the critical frequency, we get no emitted electrons. If the frequency is greater than it, we do, because as soon as one photon hits it, the electron has enough energy and it's emitted. Increasing the intensity means more photons, and then increasing the frequency past the critical frequency means we're increasing the incoming energy per photon that's greater than the work function, and that extra energy goes into the kinetic energy of the photoelectron. So by increasing the frequency, we end up increasing the kinetic energy of the emitted electrons. Fantastic. Except, wait a minute. This whole idea of particles of light this idea is completely different than the old idea that we had before. Our double-slit experiment basically proved the wave nature of light. How can light be little particles, like little BBs moving through air? How can light be these photons when we've already demonstrated that it had to be a wave in order to explain the double-slit experiment? The wave nature of light would very simply explain the constructive and destructive interference that we saw that was created by the double-slit experiment. How can light now be these little particles instead of waves? Well, that's a very, very good question. However, there was some more evidence for this particle nature of light, called Compton scattering. Compton scattering, or sometimes referred to as the Compton effect, was actually first discovered in 1923 by Sir Arthur Holly Compton, who was doing his work at Washington University in St. Louis, which I have to mention because that's my graduate school alma mater. What he noticed was that when an incident X-ray came in and struck a stationary electron, that electron was knocked off in one direction, and a scattered electron, kind of like the electrons bouncing off, being absorbed and then partially re-emitted by the electron, went off at some angle theta. Now this is very important. Theta is the angle between the incident X-ray direction and the scattered X-ray direction. If the scattered X-ray were to go straight through, theta would be 0. If it were to bounce, say, down this way, theta would be 90 degrees. If it were backscattered, in other words, if it went in, bounced off the electron and went backwards, then theta would be 180 degrees. If we solve this problem like a collision problem and we conserve energy and momentum, if the energy of the photon is if the energy of the photon is hf and a momentum of h over lambda, and we know the energy of the energy and momentum of the electron, it turns out that we find that lambda prime minus lambda, where lambda prime is the wavelength of the scattered electron, and lambda is the wavelength of the incident electron, that equals h over mc times 1 minus cos theta, where, remember, theta is this angle between the incident photon direction and the scattered photon direction. And that matched the observed results, the observed relationship between the incident and the scattered wavelengths. So that tells us that basically it does seem that these give us the correct energy and momentum, the energy of the photon that we talked about before, and the momentum of a photon, which is just h over lambda. What does this do? It seems to give more evidence to this particle nature of light. So what is light? Is it a wave or is it a particle? Well, it seems to be something that's not a wave or a particle. It's a different kind of object. We might think of it as a wave particle. It has characteristics of waves under some circumstances. It has characteristics of particles under some circumstances. And we see those characteristics depending on what kind of an experiment we're doing. If we're doing a double-slit experiment, we notice these wave-like characteristics. If we're doing a scattering experiment like Compton scattering, or maybe the photoelectric effect, or we're looking at the light being given off by an incandescent light source, we see these particle-like characteristics. Now, the Blackbody spectrum is kind of a combination. We're seeing some characteristics from the particle nature and some characteristics from the wave nature. but it seems that light has both of these characteristics. Well, if that's true about light, what about matter? Matter we usually think of as solid objects as having particle characteristics. Electrons seem to be particles. Well, is it possible that maybe matter could have wave-like characteristics as well? Could an electron demonstrate wave-like characteristics if we were to do the right experiment? Well, how did we see the wave-like characteristics for light with the double-slit experiment? Well, could we do a double-slit experiment with electrons? Would that demonstrate a wave-like characteristic? Well, maybe so.